for the space-time. So
Yeah.
it's a really good question, and I'm going to look at it. Maybe I could exchange, ideas with you. In terms of the calculation, I'm not too worried because we were confused about a number of things, and we said, okay, let's do the calculation in the proper detector frame, where it's all like much simpler, as you can see in some of the papers I sent, and we get the same answer. Exactly the same answer. So something there kind of combines in a way, I guess, that is correct. But it's a very interesting point that I hadn't actually thought about.
Yeah, I can repeat the question, or it's just for the other people here. And actually, because I think it's not only, okay, so it's probably just a confusion on my side, but it's not only kind of applies to your setup, but I think it also kind of applies to kind of actually a lot of the kind of inverse Gerstenstein realization. So maybe also Aldo has an idea about it. So my question was essentially that normally when you work in transverse traceless gauge, so you to remove the gauge degrees of freedom, first you go to Lorentz gauge, and then in the next step you use vacuum. So you use the fact that on the right hand side of the Einstein equation you have a zero to then go to the standard formulation in transverse traceless gauge. And in Majora's book, it says very clear that you're only allowed to do that if you're in vacuum. And if I think of, I don't know, a detector like LISA, right, then I can clearly understand LISA as just kind of point-like test masses in vacuum, and I can understand the effect, and it's fine to do this in TT gauge. But if I'm now kind of thinking of a scenario where I have strong electric and magnetic fields, and I'm working kind of in this conversion story, then it's not entirely clear to me if it's still okay to go to TT gauge in the usual formalism. So I should still be able to remove the same amount of gauge degrees of freedom. So I mean, I will still only get 2 degrees of freedom for the gravitational waves, but kind of the explicit form of them could somehow be naively slightly different. And I was just kind of wondering if that has an effect, if kind of this is something which is discussed somewhere in the literature, or what is going on. I mean, maybe it's completely irrelevant, right? Maybe this is some kind of higher order effect that in the end math doesn't matter. But just wasn't clear to me.
Yeah.
Can I jump in a little bit? So I just want to clarify the question a little bit. So you're saying that, okay, it's clear what vacuum is when you think about gravitational wave flying in vacuum. But if you're gravitational wave flying through some medium, like electromagnetic field as strong fields, then it's not going through vacuum. So it's still using can you still define a TT gauge, like
right.
we use in this particular background?
Right, because now if I want to do gauge fixing, right, then I have to take into account that the T mu nu on the right hand side of the Einstein equation is not 0, right? Because we have
exactly. So I've thought a little bit about like gravitational wave going through media, that and I think some other people have also thought about this, and in that way it's very similar to electromagnetic field going through medium, right? What happens is that you change the speed of light, you change the speed of light when you're going through medium, but you still keep the 2 polarization mode in the electro, if you have electric field going through medium. And I think it's similar in gravitational wave. You have a slowing down of your gravitational wave field, but you still keep the 2 polarization mode, with the additional possibility that if you have some change in the refractive index. So again, you think in terms of the E and M again. You have a refractive index. If you say going through different medium, you might have, you might gain some evanescence modes. So that would look like additional degrees of freedom. But I think it's really secretly just the same degrees of freedom, but with the wave vector rotated into the complex plane. So I think there is some. I think the ultimate question. I think you if you're going through medium, your wave vector is, you might ultimately. I'm not 100% sure, but ultimately it might just means that your wave vector has some complex terms, and that just means that you have some decaying term, which is what you expect when you're going through some medium, right? The medium can absorb the gravitational wave and excite itself, if you like.
Right, but if you have kind of like in our case here, like we would have some sort of anisotropic media, right? Because I don't know, like there's some preferred direction either in the Bose-Einstein condensate, or also like if we have a strong magnetic field, right, there's a preferred direction. So now it probably depends, like if, like the refractive index, as you call it, probably depends on kind of the angle between the incoming wave and the preferred direction of the medium. So So this is why I think that maybe, the standard formulation of the TT gauge, where you just have, the diagonal, whatever, for the plus and the off diagonal for the cross, in that very simple formulation, this I suspect may not hold anymore, right? Because it doesn't take into account this story.
So here what we have is like, I mean, the atoms, just if they did not interact, I guess, space, they would just be free falling with the space time, and that's it. But because there's interactions between them, that is kind of what gives you a like a tension between them, right? And that breaks, I guess, like the situation. But I guess what we did in the one I presented is one-dimensional. So in that case, you really need to anyway align the system with the right polarization of the gravitational wave. But now we've done some, we calculated the Bogoliubov coefficients in a 3D box. But we haven't put in vacuum, but we haven't put the atoms on it yet. And I think that is a great comment to make at this stage before we actually start doing the calculation for the phonons, because then we can start thinking from the beginning, taking that into consideration, no? But that would be, you know what, Eugene, that would be really nice if one could even see that sort of things at some point. Of course, this is very futuristic, but that if you excite these other modes, or you get this other sort of evanescent, you said some kind of modes, that would be wonderful. Oh, you're muted. Yeah.
No, we actually wrote a paper on it. Actually, we actually wrote a paper on evanescence gravitational waves from this, which is why I learned about this. But there is a paper, I'm going to show you a paper by Weinberg, one of his last paper actually, and Raphael and Flauger, where they look at propagation of gravitational wave through medium. Yeah. And they say that, and I think they have a formula about how to calculate what actually gravitational wave is when you're propagating not through vacuum. And I think they got just like quickly going through the paper, they get something like a wavelength dependent change in the velocity of the gravitational wave through this medium. And then we know that when you have a change in the velocity of your propagating medium, like just think of waves, right? And what is refractive index? Is nothing but just the fact that your wave is propagating through medium and your speed is changing, and changing. And when you get evanescence, is when you are propagating from the medium with one speed to another medium with another speed. And we remember Snell's law.
Just like in quantum optics, you get
exactly that. It's just like in quantum optics. Exactly.
So what we did, because we were discussing like a number of things, this was when we started with it. We were all learning about gravitational waves, so there was a lot of like intense discussions in the group with all the quantum opticians. How do we get these things on? But then we decided just to go to the proper detector frame, also because we were proposing an experiment and so on, and that was kind of much clearer to us. And once we finished, we got the exact same result. But I think that we got the same result by, being lucky that we were in one dimension.
I see. Okay. I mean, I really found your talk very interesting. I did not know all these things. I mean, I work with a nano optics person. You know Paco, like Francisco Rodriguez.
Where is he?
He's in KCL. He's in King College. He does.
You and I actually live in London, so we're very close. I work in Southampton, but I actually live
in London. Yeah. Okay.
So we should meet up someday.
Yeah, we should. Actually, this is very interesting. I mean, I've always been looking for analogies between quantum optics and gravitational waves, because the people who do quantum optics have so much. They know so much about wave in medium, and about gravitational wave, you always do everything in vacuum, right? Yeah. So all this technology that you all have discovered will be very easily ported over to gravitational wave in media.
We have like a lot of tools that are applicable, because once you have like bosonic fields, quantum optics has metrology, entanglement, all kinds of things in this covariance matrix formalism. That's how I've done all my work, is applying that to quantum field theory and curved spacetime, because you have the same sort of structure with the
exactly.
But also I was really like interested in the talks yesterday on dark matter and this kind of bosonic behavior, because it can be that also you can apply tools from quantum optics there, and that could be a lot of fun.
There's a wave equation, right? Wave equation in
Yeah.
medium. That's what they are. No, exactly. Yeah, no, I mean, I'm at King's. Actually, after seeing your talk, I asked my the seminar organizer to invite you to King's for a talk. So hopefully,
Oh,
you know, when
wonderful.
you
Yeah, no,
come
I'd
and
love to
you,
come and
so then so we, you know, hopefully, you know, we can have an in-person talk and we can chat a little bit more about this.
yeah, exactly. Yeah, that would be great. And because as you can see, we need a lot of help from people with your background, because, you know, we sort of done it ourselves, and it's really been very difficult because we have to learn things that are, you know, involved and so on. So then sometimes we overlook things like this that Valerie pointed out is a good point. And yeah, like I said, I thought we were lucky because we were working in one dimension. I guess in one dimension you don't see that, no, Valerie, because if you get the sort of the polarization changing, I mean, the experiment is kind of set up that you have to find the orientation. I mean, by some other means, you need to guess what the orientation should be and then align your detector in the correct way.
Yeah, I don't know. Like I don't like, it's really a question, right? So this is why I don't want to.
Yeah.
I don't want to say it matters, or I mean, it may be that it never matters, right? When maybe that it always matters. I'm really not sure. But yeah, I mean, it's yeah. So thanks a lot. I mean, I think at least for me, this was super useful. So So also, if there's any other questions that people have, maybe also like in particular the people from, if there's anybody here from like Asia and Australia who couldn't join the live discussion session last night, in case anybody has any other questions or comments they would like to make. Don't be shy. Otherwise, we can continue also discussing this question. But
I can ask something to Eugene. You have shown this. So you have shown these plots in which you. I mean, you have a few papers in which you study the collapse of perturbations into black holes.
And yep, and boson stars.
Yeah, yes, exactly. So I think you have one paper with David Marsh in which you studied the axion mini cluster.
Yeah, exactly. That's with Vidicombi and Thomas Hoffer.
Okay. So do you have in mind, but you started from a situation in which the perturbation is already quite large, right?
Yeah,
if I remember
exactly.
correctly. Do you have in mind a mechanism to get that?
No, we kind of do, but we don't. I personally, I don't believe it. It's just like what we are really interested is understanding whether or not we can form this stuff from collapse, right? And what the threshold for this collapse. I mean, if you do cosmological 10⁻⁵ perturbation, it's not going to form. It's just going to disperse. You don't have sufficient density difference to do it. So what we were interested is really where's the threshold. You know, at what threshold where you can actually collapse, and whether or not you can actually form these things, right? We always start with these objects already fully formed, and then you perturb it. But can you actually make them? Is our questions, and how big the perturbation you need to make them? Yeah. So this is what we found that yes, you can make them. Yes, you need a big perturbation to make them. So then of course if you say where does this perturbation come from? So we made up some models, which is, you know, I personally don't believe, but I think that. It doesn't stop me from writing papers. This is what my advisor tells you. You don't have to write everything you believe. But it is a question that needs answering, right? If you want to, how do you make these objects? So our answer is that the standard quantum fluctuation from inflation is not enough. You need some. It's just like the same question with primordial black holes, right? You need something more. And so where does this come from? You can always make up some model where there is some scale happening when there's some phase transition. You have a spike in your primordial perturbation. You know, there are many models of that, but
because in principle, if you have like moduli in the early universe, and say the universe is dominated by one of them, then it's behaving like matter, and perturbations can grow there.
Yeah.
So at some point, maybe you get there.
Yeah, maybe at some point, if you start early enough and they are just dark matter like scalar field that will collapse, then at some point you get there. And but we also have to be careful, because if you don't be too big, because too big they will collapse into black holes instead. So that is another one of the questions that we are interested to ask, is that, you know, what is the window, right, from the scalar field not forming, the scalar field forming, and the scalar field forming black holes, right? So where's the window? And what we normally find is that this is kind of like, we know how to form them, like just collapsing small scale simulations. What we did is that, okay, let's just assume that there's some large scale field, and then some number counts. And what we think will happen is that what you're going to find is that you're going to have a population of these boson stars. But if you find the population of this boson star, you should expect also a population of black holes. Those that not just collapse into boson star, but actually collapse into a black hole. So I think this is a generic prediction of boson stars. You cannot just form boson star, you will have to form black holes, because they are unstable.
Related to this, do you think that observing the waveforms that you were showing, say from the collision of boson stars, etc., can we learn something about the interactions?
Yes, I think you can, because I think this is related to what Fernando was asking, right? So is this okay? What are the models that you use? I think there are the details of the gravitational wave, I think, is fairly model. I wouldn't say fairly, but it is model dependent, right? I mean, if you see one of this, we should be happy. You know, you get ready for the Nobel Prize. But no, I mean, what I'm saying is that it would depend. I think that is a interesting question right now. I think it's a like second order question. Can you tell the differences between this model? I think the first order question we are trying to answer is that the difference between generic boson star and black holes is what we are at right now. I mean, going to understand the details, I think, is a second order question. We worry about that when we see one of them.
Okay, thank you.
So I have another question maybe for David Dunsky, who I see here in the participant list. So I would like, you know, regarding the gastronomy story. So does the domain wall problem ever kind of like, can you get kind of sizable, like in the domain wall string scenario, and can you actually get sizable gravitational wave signals without running into some sort of domain wall problem? I mean, I guess in the end, your domain walls are unstable, right? So in the end, to some extent, the problem goes away. But if they live for long enough, maybe that's still a problem.
Right. Yeah, so there's two scenarios with depending on whether the domain walls eat the strings or the strings eat the domain walls, which just depends on when inflation occurs relative to the strings. So the strings always have to form first. And then if you have, for instance, inflation afterwards, then you have just a pure domain wall network that will evolve. And that background energy density will grow with time, as you're saying, and you can get this domain wall problem. So the strings have to nucleate before effectively the domain walls will come to dominate the energy density of the universe. So if they don't, then you are totally excluded, and your gravitational wave signal is for naught, because you just have delta ineffective problems, for instance, from too much gravitons. So in that case, nucleation has to occur sufficiently early so the domain wall domination does not occur. In the opposite case, when you don't have inflation after string formation, so you have inflation first and then string formation and then domain wall formation, the domain walls will actually come to dominate the string dynamics before they come to dominate the energy density of the universe. And so that effectively chops the domain wall strings into pieces that will automatically decay via gravitational radiation before they come to dominate the energy density of the universe. So you don't have the domain wall problem at all in that case. Okay. So that's one's actually pretty interesting, and you can use this to solve effectively like the domain wall problem. And analogous also, there's of course the monopole problem too, right? If you have too much monopoles, you can be in conflict with, for instance, the Parker bound for magnetic fields in like the present galaxy, the present universe today, right? So not necessarily even dominating the energy density of the universe, but just too many monopoles. Even a trace amount can be deadly today. And the thing is that once, for instance, the U1 that's associated with the monopoles breaks and the strings are formed, so all these monopoles get connected by flux tubes. And so these monopoles will all decay from annihilation, for instance, after emitting from energy losses from friction and gravitational waves. So that's another way to of course get around the monopole problem. So for I guess I'm saying for the gastronomy scenarios, you get not only a gravitational wave signal, but you also get a way around these monopole domain wall problems. But for the caveat with the inflation in the nucleation cases, you need the nucleation to occur before the domain walls will actually come to dominate the energy densities of the universe.
Right, so, yeah. Right. So does that put essentially a lower? Does that put like kind of a lower cutoff on the frequency spectrum for the gravitational waves? Because
yeah, it does. So for the nucleation case, this string scale actually has to be kind of, so here's kind of like it's an issue with the tuning of scales in some sense for the nucleation, because the nucleation cases are always these tunneling processes. And so they depend exponentially on the ratio of, for instance, like for the strings and monopoles, ratio of the string scale and the monopole scale roughly, as well as, for instance, for the domain walls and the nucleation of strings, it depends on even a higher power of the ratio of the string and domain wall scales. So if you have a very disparate like hierarchy and scales, then those walls and strings can be quite long-lived. So you need them to actually be quite close together. But even then, since it's exponentially sensitive, you can get extremely long-lived walls in that case, just because nucleation just takes exponentially long to happen. And it's possible that you can, so from that you can estimate, okay, given a string tension and a domain wall tension, when does this nucleation occur? And then at what frequency does that occur? And at this frequency, have the walls dominated the universe yet? And so what's actually interesting is that you can look at, for instance, just the maximum allowed time for the walls to just right about to dominate the energy density, and then they can nucleate, because that's going to be the lowest possible frequency you can get, right? The later it happens in the universe, the lower the frequency is, because for the wall network, the typical size of the system, since they're in a scaling regime, is set just by the horizon size. So the later it occurs, the lower frequency. And even in that case, you can get, sub kilohertz frequencies and still not dominate the energy density of the universe. So that's actually pretty interesting. And you don't have to, like, you can wait sufficiently long enough and not dominate the energy density and still get lower, quote unquote, low frequency, right, gravitational wave signals. So for the other case, where strings, where walls eat the strings, and so you don't have nucleation, you just have inflation, then string formation, then wall formation, where you have just collapse scenario, that automatically takes care of the domain walls not dominating the energy density of the universe. So you don't have to put in by hand anything to ensure that it decays before, but that generally happens very early in the universe, because the decay is going to happen roughly when the walls start dominating the string dynamics, which occurs when like the size of the string wall pieces is above this critical radius, which is a ratio of the string to domain wall tension scales. And so this happens generally very early in the universe. And since it happens very early, the size of the string wall system is, roughly set by alpha, like, this 0.1 roughly or so for, the ratio of the horizon to the string size. So it's set roughly by that constant times the time at which the walls start dominating the dynamics, roughly speaking. So that happens very early in the universe. And so that frequency is generally much higher than this nucleation case. So on one hand, you don't have to worry about the walls dominating the energy density automatically, but the frequency is quite a bit higher than the nucleation case. So I guess the point is you can still get, for the strings nucleating on walls, you can still get low frequency observable signals potentially without dominating the energy density of the universe. The only caveat is that you need the wall scale and the string scale to be kind of close together so that it's not long-lived sufficiently enough that it comes to dominate the energy density of the universe before nucleating.
Okay, yeah, that makes sense. Thank you.
Yeah, for sure.
Yes. Since yesterday Mike Tobar was not in the discussion session, unfortunately, it would be nice to hear in the last 5 minutes of this session some of his thoughts about the bulk acoustic wave devices. So the typical questions we have asked yesterday is whether hi Mike, whether there are like current, what are the current open questions with respect to that technology, and what's the timeline, what are the plans that you have to improve the detector, etc.
Yeah, I guess I will talk about this in the talk on Friday, but basically it's been assembled again and running, but we're looking at I think 8 modes. Actually, I think Will, are you there, Will?
Yeah, I'm here, if you can hear me.
It'd be better if Will is the PhD student working on it. So I think it's better that he describes what's going on.
Yeah, for sure. Can go ahead, or unless you want me to go on, Mike.
No, yeah, just go and tell them the plans, because I think it's better coming from you.
Yep.
Yeah,
I suppose I'll give a little bit of an update of the current where it's at. So right now we're trying to build an identical copy, so a second detector, to put in the system to kind of as almost like an event veto. So we've got a completely second quartz crystal. We've got the enclosure built. We're just currently waiting for a new data acquisition instrument. So a new fancy digitizer. Basically, it's a hardware limitation on how many modes we can currently monitor. We have a frequency roll-off at the moment of around 50 megahertz, and it's just set by the room temperature electronics. So I think right now it's capable of monitoring as many modes as you can find under, say, between 5 megahertz and 50. So I've got about 3 weeks of data where we've monitored 8 modes across the quartz. That hasn't been looked at yet. So the future plans for it, a second identical detector. The idea being if we see events in both, we can kind of assume more knowledge about their origins. You can do stuff like orientate the detectors, put them orthogonal to each other. Monitor more modes with the new data acquisition coming in, and we also want to get some kind of muon detection system in to further veto, I guess, charged cosmic events hitting the detector as well. So that's pretty much it, I guess.
Yeah, basically the board detector is a resonant bar detector. And there's more than one mode that's sensitive, and they all calibrate differently. So we know it quite well. Maxime did his PhD on these devices and is an expert in these devices. I did my PhD on resonant bars. So in my talk, I will give about 10-minute introduction just to how a resonant bar works and how you can increase the bandwidth and all the noise sources. Because I think that's important. It seems a lot of these systems are basically equivalent to resonant bars, whether they're, like the optical spring trap type system, which is, I find quite interesting, operates like a resonant bar. So you've got, besides the noise that you get at the resonant frequency, you have the thermal noises shaped by the transfer function. Then you have the readout noise, which is very important. So what you use as your transducer has a big effect on your sensitivity, how you read out your gravity wave. In our system, we are lucky that the capacitive output impedance of the electrodes which read out the ball sort of matches well to the inductive input of a squid. But these impedance matching type, back in the day of the resonant bars, this impedance matching of your transducer to your resonant system is very important. So I'm not sure if that's totally considered in the systems I've seen at the moment, which act like resonant detectors.
Okay, thank you very much. So I think it's time to switch over to the